All right, so we're just 15 minutes of lecture today, and then the quiz will release. I'm just going to try and finish up lecture set number 7 so that we can start after reading week with a new set, and you have all the material you need for assignment number 4. We are working through an illustration where we are computing the margins of errors for the multiple comparisons that fall out of a two-way ANOVA. So in a two-way ANOVA, we have two main effects and we have an interaction effect. So that means that we can have multiple comparisons for each of the main effects and the interaction effect. So in part A, we're doing the margin of error calculation for the multiple comparison of the two types of clubs. So once we have the margin of error, all we have to do is take the difference between the averages for the two clubs and then check to see if this is statistically significant, or check to see if the interval contains 0 or not. Same thing for the golf ball brand. So in part B, we did a calculation for the golf ball brand to determine if there's evidence of a difference. Okay, and then in part C, we are now doing it for each of the interaction effects. So I started this a bit early just to make sure I'd have time to finish it. The process is the same. So we have an experiment-wise error of 0.05. Little m is k choose 2. We have 8 different treatment interactions. So we have 8 choose 2, which is 28. That means that our alpha I for the comparison is going to be alpha e over 2m, which is 0.00089. In step 4, I've ordered the treatment means. These treatment means are on the same page as the other means, so slide 27. And now we're going to compute the margin of error. Okay, so here we're going to have T alpha I DFE times the square root MSE 1 over little n AB IJ plus 1 over little n AB IJ. Okay, so this is going to be a T on 0.00089 and 24. So 34. And then each treatment combination only has 4 observations, which are the number of replications. Okay, so then this value will be equal to 8.155. Okay, so once we have the margins of error, the last step is to determine where the differences exist. So we've all seen illustrations of how this would work. We have to do this for each of the main effects and the club effect, whereas in our previous illustrations, we've only had to do it for one treatment effect. But the process is the same. So we basically take the difference between each pair of means and compare it to the margin of error. If the difference is greater, if the absolute difference is greater than the margin of error, that's going to give evidence of a difference. Likewise, if the margin of error is less than the absolute difference, that would give evidence of a difference as well. Okay, so on slide 32, we have the results from all of the multiple comparisons. Okay, so what we are going to do here is determine where the differences actually lie. So first off, starting with brand, remember that anything that is connected or has 2 dashed lines that are beside each other represents no difference. So this is saying that A is not different from B, A is not different from C, A is not different from D, and B is not different from C. Okay, so that would mean that B and D and C and D are giving average means that are different from one another. Okay, so for brand, we could say at the 5% significance level, the data provide sufficient evidence to suggest that the average distance traveled is different between golf ball brands B and D and C and D. Okay. Okay, and then for the club and for the treatment combinations, we can have a similar conclusion in this case. So for example, for the club effect, if we go back and we look at the diagram for club, you can see that we only have two clubs, which are driver and 5-iron. Those are not connected, which would mean that they are different. So here we can say, at the 5% significance level, the data provides sufficient evidence to suggest that the average distance traveled by a ball or by balls by golf balls hit with a driver and 5-iron are different, which is not overly surprising if you're familiar with how golf works. Okay, and then finally, for the treatment combinations, so I'll say for the interaction, we can say at the 5% significance level, the data provides sufficient evidence to suggest that the average distance traveled is different between golf ball brands, is different between golf ball brands. This one is actually quite different. I guess so what we can say is different. Traveled by golf balls is different between, and then we have a, oh, and then if we go back, we can see here. So within the driver, there's quite a bit of similarity. Within the 5-iron, there's quite a bit of similarity. Again, the treatment these interactions are showing us that all the driver distances are different from the 5-iron distances. So that's the same conclusion we had for the club effect. So if we're focusing specifically just on the interactions here and not going across driver and club, we could say between the driver A combination and the driver C combination, the 5-iron B combination and 5-iron C combination, and the 5-iron B combination and 5-iron D combination. Right. But again, and you can also say, you could also summarize and say in between all driver and 5-iron interactions, but that's again summarized by the club effect. So I'm in this particular case, I'm focusing just on the inside the driver and or for the driver and for the 5-iron separately, because we know that driver and 5-iron create a significant difference on their own. Okay, so the last thing I want to talk about fairly briefly is just the residual analysis for a two-way ANOVA. Very similar to the residual analysis for a one-way ANOVA or a completely randomized block design. Okay, so in the table below, I give the residuals for each of the interaction effects. You can verify these values by using the statistical model that was given for the two-way ANOVA. So I've left that as an exercise. Now, in terms of utilizing the residuals, it's not very different from what we had done before. So we would create a QQ plot. So this QQ plot here, or normal probability plot, is showing all of the residual values against the quantiles of the normal. So it's one plot for every normal quantile. And then in the second plot, we have a residual versus fitted value chart. This would be the same thing as doing a box plot of each of the treatment combinations. So these are actually stacked lines. So for example, we have 4 stack points here. We have 4 stack points here. We have 4 stack points here, 4 points here. We have 4 points here, 4 points here, 4 points here. Okay, and with this plot, all we're doing is checking to see if it seems like the range is the same between the treatment combinations, which it clearly isn't. And we can also see that if we take the max standard deviation and divide by the minimum, we get 4.7, which is much larger than 2, which would indicate that the variance isn't constant. So we can say here, very briefly, no evidence to suggest that the normality assumption is violated, but we do have, there is evidence to suggest that the variance between treatment combinations is not constant. Okay. Okay, perfect. So that brings us to the end of lecture set 7. So we've covered all of the ANOVAs that we're going to talk about in the course. When we return from reading week, we will start with non-parametric statistics, which is it's a shorter unit, but it's a very fun unit. So we're going to look at alternatives to the 2 sample t-tests and 1 sample t-test and the ANOVA that don't require the normality assumption. So those would obviously be beneficial in many situations because normality is typically not as common as we might like it to be. Assignment 4, I believe, is due after the break, and that covers the ANOVA material. So you have everything you need to complete that. And quiz 2 will release in about 40 seconds. So I will be in the office hour room if you have any questions, and otherwise have a good reading week. And I look forward to meeting you in person after said reading week. Okay, so good luck on the quiz and chat with you then.